couple of quick updates, right? We've got, I actually moved it on Canvas, the learning celebration to Wednesday. And it will cover over up to what we did on Wednesday, which was the concavity stuff. So the stuff we're going to talk about today and Monday, no. Let's see what else. I thought there was one other thing I wanted to tell you guys. I think that's it. So anyway. All right, so what we're going to start today, and we'll continue it on Monday, is optimization. So basically, we've talked about the first derivative test, second derivative test, those sorts of things, right? Oh, actually, no, there was we needed to do that last example from the very end last time before we get to it. So, okay, so let's do that real quick. So we had this function from before, 40t cubed minus 5t to the fourth minus 4t to the fifth. Okay, so on Monday, we found the critical points and the maxes and mins and all of that stuff for this function by only using the first derivative, right? So take the first derivative, set it equal to 0, find the critical points, divide up the number line, pick some test points, figure out what's going on in each interval, and then that tells you what is happening at the critical points, max, min, or neither, right? Okay, so Gucci with that, right? All right, but we could also use the second derivative to help us. So we still need to do the first derivative and set it equal to 0 to get the critical points. What happens after that is the new thing. Okay, so what was the first derivative of this thing? Yeah, minus 20t cubed minus 20t to the fourth. And we said, okay, let's be smart. Oh, yeah, that's what I meant to do. And I think we factored a minus 20. Oh, by 60, I mean 6. Okay, good. Yeah, and then the quadratic piece factors, and so what did we get? T squared minus 6 plus t, so that'd be t plus 3, t minus 2. Yeah. Okay, so what are our critical points?
0, 2, negative
3. Yeah, 0, 2, and minus 3. Okay, so all of that's the same as when we did this one on Monday. But we've now come to like a fork in the road, and on Monday we went down the first derivative test route, but we could also have gone down the second derivative test route. It will give us the exact same information, it's just how we get that information, okay? And in some cases, doing the second derivative test route is easier, I think. And in other cases, the first derivative test is easier. It just kind of depends on the particulars of the function. Well, first off, we need the second derivative, which would be, 240t minus 60t squared minus 80t cubed. And like before, we can factor, right? So let's pull out what, a 20, a minus 20. All right, so a minus 20t, and then what else do we have? So that would leave a 1, that would leave a 12, Yes, thank you. A negative 12, a plus 3t, and a plus 4t squared. Well, I guess I could also pull out a, no, I can't, because 3 is prime, and 4 is definitely not. Okay, so, good? Now, I could try to factor that last term, but it actually, I don't really care, because I don't really care where the second derivative is 0 for determining max and mins. If we wanted to also know inflection points, we'd need to do that, but we don't in this case. So all I've got to do to determine whether or not my critical points are maxes, mins, or saddles is plug each of them into the second derivative and see what we get. Okay, now this part of it is something that at first feels wrong and feels backwards, but if you think about it, it's actually correct, okay? Which concavity goes with the maximum? Positive concavity or negative concavity? Negative, but you'd think it'd be positive, right? Okay, now let's sort of think about why negative concavity goes with the maximum, because what does negative concavity sort of look like? Looks like that, right? Where there's a maximum. And positive concavity would look sort of like this. Okay, so like I said, it feels backwards at first, but if you sort of draw a quick sketch, it's like, oh, yeah, of course. All right, Gucci. And where's Mr. Grimmett? I have to send him a nasty gram. We have anybody online this morning? Not on Twitch yet. Okay, so I just need to plug these things in. So let's do f double prime of 0. Well, that one we get 0. Okay, that's easy because of the 0 out front, or the t out front, excuse me. Okay, so we got 0, great. So that means that the point x equals, or sorry, t equals 0, it's neither a max nor a min, okay? Right, nothing special. Okay, so it's actually a point of inflection. Okay, or actually, just to kind of start to prime your brain, another name for that is a saddle point. And in particular, those of you guys who are going to go on and take Calc 2, when you start to look at this from a multivariable context, saddle is actually a really accurate word for it, because a saddle point for a two-dimensional thing looks sort of like this. It's like a Pringle, right? And, you know, this looks kind of like a horse saddle, right? You got the front part, and then your legs go out the side. So, yeah? Yeehaw. How many of you guys have ever ridden a horse? Yeah? No? You're what do you mean? You either have or have not ridden a horse? Well, anyway. Okay, so we got to do the same thing for 2 and minus 3. And again, I don't really care about the specific number I get. I just care positive or negative. Okay, so if we plug in 2, we know that this first term is negative because of the minus sign. What do we get if we plug in 2 here? And again, I don't really care about the value. I just care about the sign. 2 squared is 4, times 4 is 16. 3 times 2 is 6, so I've got 16 plus 6 minus 12, definitely positive, right? So I've got a negative from the first term and a positive from that quadratic term, so f double prime of 2 is actually negative, okay? Good? Which means 2 comma whatever f of 2 is a local what? Negative? Max, yeah, see? Gotcha. Okay, it feels backwards, but it isn't. Right? Ah, we were wondering if you'd make a guest appearance. Oh, you've already been here. Your bag's here. Okay. I was about to start sending text messages because the class, we have been really, I used this on a guy yesterday that was running a little late, asking him if he's going to come to class, but also we have been trying to reach you about your car's extended warranty.
Yeah.
Yeah.
Pretty sure it's
Yeah. Okay, so let's do the same thing with, what was it, -3? Okay, and again, I just care about the sign, so I plug it into the first part. This first part's going to be positive for sure, okay? -3 squared is 9 times 4 is 36. So we got 36 minus 9 minus 12, definitely positive. And so -3 comma f of -3, whatever the y value is a local min. Okay, positive second derivative means that you, this helps if I put the right hand gesture up, right? Positive second derivative means you went through a minimum, not a maximum. Okay, good? So, here's kind of my rule of thumb for when you choose the first derivative test versus the second derivative test. This function that we started with was just a polynomial, right? Taking derivatives of polynomials is not bad. And in fact, it's almost easier to work with the second derivative of a polynomial than the first derivative because the degree goes down by 1 each time you take a derivative, okay? So, and smaller degree polynomials are, of course, easier to deal with than bigger degree ones. So for a polynomial type function, I'd probably do the second derivative test. Yeah, like I said, in general, okay? Where I would probably not do the second derivative test is, what about if the function is like a fraction or it's got some square roots or something like that, where taking the first derivative might be kind of a pain, and then going and taking the second derivative after that might be even more of a pain, right? So if the function's kind of nasty, then I'd probably not want to do the second derivative test, if I could avoid it. Okay, but the good news is, either way you go, you will get the same answer and the same information. It's just which way do you want to get to it. Okay. Now, if you also are worried about inflection points, you have to go to the second derivative anyway. And so you might as well use it once you've got it, right? Yeah, so you've got sort of a choice that you can make there. Okay, so what the first derivative test, the second derivative test, what this will gets us, right, is the ability to tell local maxes from local mins, okay? Yeah, okay. I don't know how long that's been off. I think the battery's about to die again. Great. Okay, so 1,000 minus 2x with the 1/3. Okay, so now what do we need to do? Take a derivative, but what would maybe be a good idea first? Yeah, distribute it. All right, so what are we going to get? 1,000 over 3x minus 2/3 x squared. Okay? So next step is what? Yeah, and what do we get? 1,000 over 3 minus 4/3 x. Okay? And so if I solve for x, oh, sorry. What do I do? What do I want the first derivative to equal? 0. Okay, so if I set this equal to 0 and solve for x, what do I get? 3/4 times the 1,000 over 3, which happens to be 250. Okay, that's nice. Good? Okay, so if x is 250, what's y? Well, if we spend 250 on the bottom piece and 250 on the top piece, that leaves us with 500 meters worth of fencing left. Okay? For how many pieces? So 500 over 3 would be y. Okay, and then this would be 250 meters. And so y equals 500 over 3 meters, whatever that is, 133 or something like that, and a third. Okay, does that kind of make sense? Yes? Oh, you solve for x instead of y?
No, I solved for y.
Okay.
You get stuff. Oh no, yeah, you solved for x.
Yeah, no, we solved for y.
Yeah.
Okay,
Yeah,
sorry,
no,
we solved for.
But the 3's canceled out, didn't they?
Right. Okay. So the derivative is this, right? Or sorry, that's the objective function. Are we good? Okay. So I took the derivative. The 3's don't. Oh, I see what you did. If you just set this equal to 0, you could multiply both sides by 3 and just get rid of them.
Like from the objective function, there's a 3y.
3y.
Yep.
Here?
Wait, oh, so the objective function doesn't care you put 3. Okay.
Yeah.
Okay.
Yeah. Yeah. Now, okay, so let's go back. When we solved the constraint to get y in terms of x, we could have solved for x in terms of y instead. Okay? There it doesn't really matter which one you do. So my rule of thumb is I pick the one where the algebra is going to be a little easier, right? Or where maybe some numbers cancel and simplify nicely, but it doesn't really matter, okay? Okay, so are we cool? How do I know that I've actually found the maximum here, other than because we're not idiots? Right, what's the step that I haven't yet done? Yeah, either the first derivative test or the second derivative test. But in this case, what's the second derivative? It's a negative 4/3, which is negative. So like the last problem, we know we definitely have a max. How would you minimize the area of the paddocks? Well, basically, yes, right? You, I mean, you say it that way, and that sounds flippant, but in fact, that's exactly right. You make one of the dimensions 0, which is tantamount to not building a paddock. Okay. Now, the other way you would minimize is, so strictly speaking, the constraint I wrote, 2x plus 3y equals 1,000, Strictly speaking, I should have put less than or equal to 1,000 because nobody said that Owen had to use all 1,000 meters of available fencing. It's just that he couldn't use more than that. Okay, but we're not complete idiots. Owen wants to maximize, like, why would he leave fence on the table, so to speak? Right? Not using all of the available fencing is probably a bad idea. Okay. All right, so does that kind of make sense? All right, so Monday we're going to do more spicy versions of this, right? We're in like honey barbecue territory, but we got to get to the Carolina Reaper, blazing challenge. Okay, so that's fine. Yeah. All right, see you guys later. Have a great weekend. Oh, and what's going on today? Vaccine clinic. No 5G microchips, I promise. Although they're actually pretty sweet. So.